Alright, these are the notes for section 2 of chapter 1, variables and quantifiers. So the main idea of this section is basically what a statement is and how you can quantify it to make it either true or false. So a statement in math, well really an open statement in math, is just any like equation. You have x equals 7 plus 9, that's an open statement. 27x to the 50 over 0, that's still, even though it's undefined, it's still an open statement. You haven't actually done any math with it. But then, if you want to actually define if those statements are either true or false, they actually carry any meaning, but you have to quantify the statement in some way. And there's 3 major quantifiers. The first one is an upside down capital, looks like an upside down capital A, and it means for all. And this would just be used in any case where the statement's always true. So an example of that would be for all, so you have for all x that are in natural numbers, I guess, x plus 1 is greater than x. So this is pretty obvious. Natural numbers 1, 2, 3, 4, 5. Obviously 5 plus 1 is 6, which is greater than 5. You can say that for any natural number. The next one is, looks like a backwards capital E, and it means either for some or there exists. This just means as long as it's true in at least one case, the statement is true. So at least there exists where x is in the set of natural numbers. There exists a natural x such that, if you want to use such that, remember you can use a colon, such that, or another one that you can use would be a backwards epsilon. This also means such that x plus 1 equals 7. And we can use our pre-algebra brains and say, yeah, x plus 1 equals 7, that means x is 6. Which means there definitely exists a natural x that when you add 1, 2, you get 7. But it's not true for all of them, just that one case. So yeah, you can definitely say it exists. The last one, there does not exist. It's like it's like the backwards E. This is, yeah, does not exist. Does not exist. Oops. Actually, I guess the better way is for none, or no. For none or for no. Or, I guess, yeah, it doesn't exist. There doesn't exist. And so this would be using a case where you're working with a statement that's demonstrably false in all circumstances. So you could say there does not exist. Let's just keep up with the natural numbers. There does not exist a natural number such that x is in the set of, I guess we could go with negative integers, because these are 1, 2, 3, 4, 5, and negative integers, all of them are negative numbers. You got -1, -7, -506, so on. So there's never going to be a case where this statement is true. Just one other extra tidbit of information that might be useful to you. This is more relevant to the last unit, but still useful to know. If you have a set, let's say the set 1, 2, 3, and it goes to 8. It's pretty clear there's 8 items in the set, 1, 2, 3, 4, 5, 6, 7, 8. If you wanted to figure out how many subsets you can make, you could either go through painstakingly, empty set, subset is 1, 2, and so on, but that would take way too long to figure out by hand. Instead, you could use another trick and figure out that for every item they have in the set, so you have 8 of them, you can take 2 to the 8 items, and I think that's 256 if I remember correctly. There's 256 possible subsets from this, and that includes the empty set and that includes the improper set, which, as a reminder, the improper set would just be basically saying the same thing over again. I guess we would say is a member of. This is the improper subset of this because they're the same exact thing. But when you include the empty set and the improper subset, you hit 256 sets. This has to be true. Just have you just have the set of 1, just that. Yours going to be 2 to the 1 sets you can make. And that would be much easier to figure out by hand. It's just empty set and the set containing 1. I think that's all that gets covered in this unit. And so that's it for the notes. Bye.